Knowing what the components of the solid Earth are isn't enough to answer many questions about our planet. In addition, geologists need a timescale, which organizes in chronological order rocks and geologic events. Specifically, a timescale allows for comparisons between rocks in different areas and facilitates connections between causes and effects. The development of the geologic timescale relies on two different approaches: relative and numerical dating. Relative dating places events in order, while numerical dating specifies an age. Each method has its own strengths and is useful in different scenarios. To create a geologic timescale, they must be used together. The lecture for Chapter 1 briefly discussed the earliest history of geology, but geology as a recognized science is relatively new, with its foundations in the 17th century. At that time, many scientific breakthroughs were being done by physicians, who in many areas were among the few educated people. Nicholas Steno was a Danish physician working in Italy who first formalized three of the basic geologic principles: superposition, original horizontality, and lateral continuity. Now, individually, these strike me as just common sense, but it's the application of these together and with other principles I'll mention in a minute that allows for the geologic timescale to begin to be developed. Superposition refers to younger sedimentary rock being on top of older sedimentary rock, unless the area has been overturned or folded. This principle is really simple. Younger sediments can't be inserted under pre-existing rocks. Original horizontality says that sediments are laid down in flat horizontal layers. Well, more accurately, the layers will appear horizontal to the eye. In reality, there is usually a very tiny slope that is exaggerated in the image shown here. So that means that anytime you see the fold, such as this one, some event had to occur after the rocks were deposited in order to bend them. Lateral continuity refers to the fact that sedimentary rocks are originally laid down in layers that extend in all directions until they eventually taper out. Now, these layers can extend for thousands of miles. However, erosion can cause gaps in those layers. James Hutton is commonly called the father of modern geology and wrote what is effectively the first book on geology, Theory of the Earth. In that book, he put forth the idea of Uniformitarianism, which says that the present is the key to the past. Events that occur today also occurred in the past, because the laws of nature don't change. This was in contrast to the then held view of catastrophism, which states that all geologic changes are the result of rapid natural disasters. Now, unfortunately, many books and websites set up the terms uniformitarianism and catastrophism as completely contrarian ideas, where catastrophism says all geologic change occurs rapidly, and uniformitarianism says all geologic change occurs slowly. However, keep in mind that any physical event that can occur today could have occurred in the past, and that does include catastrophes such as large rocks smashing into the earth, devastating ecosystems. So in reality, uniformitarianism does not say all events occur slowly. It allows for both rapid and slow events. William Smith was the engineer who created the first geologic map for a large area. To assist in building canals across England, he created a map of the rocks that were known and was able to interpret what to expect in areas where rocks were not exposed. During this process, he noted that fossils occur in a definite sequence that is repeated in other areas. This principle of fossil succession allows us to use some fossils to determine the age of rocks. In the case of fossils of trilobites, they are always found in rocks older than those with fossils of dinosaurs. Globally, there is never an exception to this pattern. trilobites go extinct before dinosaurs appear. However, some fossils are not as useful for relative dating. A group of animals called brachiopods lived at the same time as trilobites, at the same time as dinosaurs, and are still around today. So finding fossil brachiopods does not say much about the age of the rock in which it is found. Now, in practice, geologists would identify the fossil to the species level to more precisely be able to date the rock. Charles Lyell wrote what is essentially the first textbook of geology, and in it he proposed two additional geologic ideas: the principle of cross-cutting relationships and the principle of inclusions. The principle of cross-cutting relationships says that a rock or feature must be older than the event that broke it. That event can be a fault, the intrusion of magma, or erosion. Now, be sure that your video is maximized so you can see the details on this slide. In this illustration, we know that the sandstone is older than dike A because the dike cuts through the bed of sandstone. We also know that the batholith is also younger than the sandstone because the sandstone had to be there before it could be cut into by the magma that formed the batholith. However, which is older, dike A or the batholith? Now we can answer that by chaining events together. After the sandstone was deposited, it was cut by a fault, which was then cut by the younger batholith, which was cut by the magma creating dike B and the sill, which was cut by dike A. Therefore, the batholith is older than dike A, and dike A is younger than everything on the screen except for the erosion that is currently happening at the surface. Inclusions are fragments of rocks that have been enclosed within another rock body. This can happen in a couple ways. Magma can intrude into pre-existing rock and encapsulate bits of the older rock, or existing rock can be weathered and incorporated into newer sedimentary rocks. Unconformities are gaps in the rock record. The three types discussed in your textbook differ by the type of rock that is eroded before deposition of sediment resumes. Angular unconformities occur when the erosion happens on tilted or folded sedimentary rocks. Nonconformities occur when the eroded rock is igneous or metamorphic. Disconformities occur when the eroded beds are horizontal sedimentary rocks. Now, there is a fourth type of unconformity not mentioned in your textbook. Paraconformities occur when there is no erosion, but no rock is being deposited, so there's still a gap in the rock record. This is by far the most common type of unconformity, but it's also the hardest one to identify. Knowing the sequence of events in one area is not enough to create a geologic timescale, because no single place preserves all rocks and all events. Instead, geologists need to piece together rocks and events in different areas by using correlation. The most basic correlation relies on the principle of lateral continuity to connect different areas. Your book uses the example of national parks in Arizona and Utah. The uppermost rocks in the Grand Canyon correlate to the lower rocks in Zion. The uppermost rocks in Zion correlate to the lower rocks at Bryce Canyon. So even though there is no overlap between the Grand Canyon and Bryce Canyon, we can still determine that the rocks at Bryce are younger. The type of correlation used to connect the parks in Arizona and Utah was lithostratigraphic correlation, meaning that it relied on the types of rocks. But there are many ways to make connections between areas. The other two most common methods are chronostratigraphic and biostratigraphic. Chronostratigraphic refers to the connection of indicators of time of particular events. For example, an asteroid impact can be recorded globally. Biostratigraphic correlation uses fossils. That brings up the question of what fossils are. There's actually not a universally accepted definition. Some geologists will say that a fossil has to be at least 10,000 years old. Well, that's an arbitrary definition. Some people think fossils have to be altered in some way to make them different than their form in the living organism. However, there are many fossils that are preserved in an unaltered state. Tooth enamel and oyster shells are examples of stable materials that can last for hundreds of millions of years without changing. So I prefer this somewhat vague definition. A fossil is any kind of evidence of prehistoric life. Biostratigraphic correlation uses fossils, but only ones known as index fossils. Your textbook defines index fossils as those with a wide geographic range but a short geologic range. There are two additional characters. Index fossils must be abundant and easily identified. Now let's move on to numerical or absolute dating. At this point, we start to specify an age instead of just saying rocks or events are younger or older than other rocks and events. People have long tried to create estimates for the age of the Earth, and some of the first scientific approaches measured how long it took iron to cool and solidify. Obviously, the Earth is not only made up of iron, but in general, that's a good model. The time for different amounts of iron to cool was extrapolated to the size of the Earth, and the first estimate for the age of the Earth was about 75,000 years. Now, this approach was redone with many additional masses of iron to create much larger estimates of 24 to 40 million years. The MA on this slide stands for mega-annum, which means millions of years. Now, there are several reasons why this age is still too low. Radioactivity in the Earth creates heat. The sun adds a little bit of heat. Gravitational pulls from the sun and moon generates a little heat. And materials move inside the Earth, meaning that Earth does not cool like a ball of iron. Around 1900, several studies looked at the amount of salt being added to the oceans by rivers and calculated that it would take about 100 million years for the oceans to reach their current level of saltiness. Now, this simply gives a minimum age for the Earth because not only is salt being washed into the oceans precipitate salt in the form of the mineral halite. In 1860, geologists estimated how long it would take to form the known thickness of sedimentary rock. It was determined that it would take about 3 million years to create what was known at that point. Now, even then, geologists knew that this was not going to be an accurate estimate of the age of the Earth. Erosion happens, and it's impossible to estimate how much rock has been eroded in any particular area. Plus, the known thickness of rock at that point was based almost exclusively on rocks in England. Now, this method was redone in the 1900s based on better global estimates on the amount of sedimentary rock. This estimate of 1.6 billion years, the GA is an abbreviation for giga-annum or billions of years, still does not include the unknown amount of eroded rock. So this is also an underestimate. Radioactive decay was the big breakthrough in numerical dating. And for more than the past century, geologists have tried to date as many things as possible to find the oldest materials. Currently, the oldest rocks known from Earth are about 4.3 billion years old. As you know from studying the rock cycle, rocks are formed from previous rocks. The oldest crystal from Earth is about 4.4 billion years and occurs as grains within a sedimentary rock that formed much later. The age of the Earth is estimated at 4.6 billion years. So how can the age of the Earth be older than the oldest known piece of the Earth? It's based on meteorites. Meteorites were formed at the same time as the other solid chunks of our solar system, including Earth. And meteorites all date to about 4.6 billion years. There are many methods of numerical dating. Perhaps the simplest is using dendrochronology, or tree rings. In the vast majority of years, trees will create a set of light and dark rings. If you count the rings, you know how much time is represented by that piece of wood. By matching events preserved in wood, such as fires and droughts, connections can be made between living and dead trees. In most areas, this gives us a good chronology for about the last 10,000 years. In a few areas, dendrochronology can give ages as old as about 26,000 years. Most numerical dates on geologic events are from radiometric dating. Carbon dating is one type, and it is useful for dating objects less than about 40,000 years. However, if the object is older than that, carbon dating doesn't tell us much. For example, carbon dating is never useful for dating a dinosaur bone. Fortunately, there are other radioactive materials with longer half-lives that can be used for dinosaurs. The half-life is the amount of time for half of the parent material to change into daughter material. After about 8 half-lives, there is so little parent remaining that the age can no longer be determined. There are many radioactive isotopes with half-lives ranging from a tiny fraction of a second to billions of times longer than the universe has existed. So the key to getting numerical dates from radioactive decay is choosing the right parent material. Before you take the quiz on this chapter, be sure to go through the sample radioactive decay problems within this module.